Hello! In this video we're going to talk about the fundamental theorem of finite abelian groups. In many of the previous videos we've taken a look at this table, which is found on MathWorld, which is a Wolfram Web resource. In this table we have listed the finite groups of orders 1 through 31, divided into columns based on whether they're abelian or non-abelian, but each group of one of these orders is isomorphic to something in this list. Now we've noticed many patterns in this table. We've talked about some of them in past videos, and today we're going to take a look at what happens specifically on the left side of the table with the abelian groups. Now the main thing we notice is that every group on the abelian side of the table is either cyclic, which is what the table uses C to stand for, or it looks like the direct product of cyclic groups. Now, leading up to this, we've seen a couple results which kind of fit in with this pattern. We've seen that every group that has an order P, where P is a prime number, has to be isomorphic to ZP, the cyclic group of order P. We've also seen that every group having order P squared, where P is a prime, is isomorphic either to the cyclic group ZP squared or to the direct product ZP, direct product ZP. We've also learned about Cauchy's theorem. Now that says that if G is a finite group and P is a prime dividing the order of G, then G has an element of order P. Now of course having an element of order P means that there is a cyclic subgroup of order P, so again we see this idea of groups or subgroups with prime order. Finally, we talked about the groups U of n, the groups of units modulo n, those numbers that are relatively prime to n, that are less than it, and greater than 0. We showed in a previous video that every group U of n is isomorphic to the direct product of cyclic groups. Now this took a couple steps. We showed that based on the factorization of n, you could decompose U into a direct product of other U groups, and then using results of Gauss, we were able to take each of those U groups and show that it was isomorphic to a cyclic group or to a direct product of cyclic groups. Well, these results have all been building to a crescendo, which is arriving right now. As we take a look at the list of abelian groups, we see that each one can be written as a direct product of cyclic groups of some kind. Let's put this in a theorem. This theorem is due to Kronecker in 1858. We call it the fundamental theorem of finite abelian groups, and it states that every finite abelian group is isomorphic to a direct product of cyclic groups with prime power orders. Now, it's true that the number of terms in the direct product, as well as the orders of the cyclic groups, are uniquely determined by the group. Now, what is this saying? Well, in the table from MathWorld, we saw that for groups of order 11, there was only one such group. It was the cyclic group of order 11. For groups of order 12, at least on the abelian side, there were two possibilities. Each is a cyclic or the direct product of cyclic groups. Now, neither 12 nor 6 is a prime power order, so we should explain that. You'll remember, though, from our earlier videos that Z12 can be written as the direct product of Z4, direct product Z3. We can do this because 4 and 3 are relatively prime, so we can decompose the cyclic group in that way. For Z6, we can take Z6 and express that as Z2 direct product Z3, so the direct product Z2 direct product Z6 can be written as Z2 direct product Z2 direct product Z3. Now we'll point out that the order that we list these factors in a direct product doesn't make a difference. If I were to take the group Z3 direct product Z4, then technically it would be a different group to this one, but it would be isomorphic to it. And the fundamental theorem is a statement just about isomorphisms. Well, this tells us an awful lot. It tells us that it was not a coincidence that the left-hand side of this table had so many direct products and so many cyclic groups. We're going to see a couple more applications of this fundamental theorem. First, we can use the theorem to come up with all the groups of a given order, all of the abelian groups of some finite order. So for instance, we can answer the question, how many abelian groups are there of order 125, and what are they? Well, the theorem tells us that every finite abelian group can be written as a direct product of cyclic groups of prime power order. And we know that in a direct product, the order of the group is the product of the orders of the groups involved in the direct product. So since 125 is a power of 5, we will be looking for the ways of breaking 125 as a product of other factors. Now we can write 125 as either itself, or we can break up those 5s as 25 times 5, or we can break it into 3 pieces, 5 times 5 times 5. There's no other way to take the factors of 125 and group them. Remember, the order that we write these in doesn't matter. So writing 5 times 25 gives me the same result as writing 25 times 5. Now, if I were to take these numbers, I will see that I can build a direct product of cyclic groups in a way corresponding to each. For the number 125, I can find a cyclic group of order 125. For the numbers 25 and 5, I can write a direct product Z25, direct product Z5. And for 5, 5, and 5, I can find a corresponding group Z5, direct product Z5, direct product Z5. Now, in general, when you have a finite abelian group of order p to the k, where p is a prime, then we will have one abelian group we can build for each partition of that exponent k. The reason why we had 3 different groups here was because there's 3 ways to take that 3 in the exponent and break it up. We can either write 3 as 3, or we can write 3 as 2 plus 1, or we can write 3 as 1 plus 1 plus 1. And that told us how many 5s to include in each factor. The integers that we break the 3 up into become the exponents in the powers of 5 in the subscripts. We have 3, we have 2 and 1, and we have 1, 1, and 1. Let's see this applied in a slightly more complicated example. Let's suppose that we wanted to list the abelian groups of order 144. Now we're going to use this fact about the partitions of the exponents of prime factors. We'll take 144 and write it in its prime factorization as 2 to the 4th, 3 squared. And then as we take a look, we'll see that 4 can be partitioned into 5 ways. Namely, you can take 4 by itself, you can break it into 2 pieces as 3 plus 1 or 2 plus 2. You can break it up into 2 plus 1 plus 1, and you can break it up as a sum of all 1s. For 2, there are 2 ways of partitioning that. You can either keep it together or break it up. Now, for these ways of writing 4 and 2, I'm going to build my factors, my ways of breaking 144 up accordingly. We'll end up with 10 different finite abelian groups. 10 is 5 times 2, and you'll notice that each of these groups corresponds to a choice of one of these partitions of 4 and one of these partitions of 2, and we'll remember that the 4 is the exponent on the 2, and the 2 was the exponent on the 3. So for instance, I might take 4 and 2, and if I were to use that, I could form the direct product z 2 to the 4th direct product z 3 squared. This is z16 direct product z9. If I were to take 2 plus 2, say, and 1 plus 1, that would give me z2 squared, z2 squared, direct product z3 to the 1, 3 to the 1. And in general, there's one group for each way of choosing a partition of 4 and choosing a partition of 2. Now, by the fundamental theorem of finite abelian groups, we can be sure that this list contains all the groups that are abelian and of order 144. Each of these groups is distinct from the rest. No 2 of the groups in this list are isomorphic. Now, as another application of the fundamental theorem, we can also take a finite abelian group and recognize it as one of those groups that we're familiar with, those cyclic groups or direct product cyclic groups. This is a group of order 8. As you look at the Cayley table, you'll see that it is abelian, and you may know already which group this is isomorphic to. But what does the fundamental theorem say? Well, the fundamental theorem of finite abelian groups, or MathWorld's table if you like, tell us that there are 3 possibilities for abelian groups of order 8. One is the cyclic group Z8, The other is the direct product Z2 with Z4. And finally, we can take the direct product of Z2 3 times. Which of these possibilities is this group isomorphic to? Well, delaying that question for a little bit, let's note that you can recognize groups from their element orders. If I were to list all the possible abelian groups of order 16, I'll come up with 5 groups, and here they are. It turns out that different direct products lead to different orders among the elements of the group. To illustrate that, let's take a look at the list here. Now, the group Z16 has a generator. It's a cyclic group, so there should be an element of order 16. And in fact, there are 8 elements of order 16. So if you have a group that has order 16 and it's abelian, and you want to know which of these 5 groups it's isomorphic to, you might start by looking for an element of order 16, and if you find one, you'll know that you're looking at the group Z16. Now, if you didn't find an element of order 16, you might find an element of order 8. And if you did, you'll see that the second group is the only group that does not have an element of order 16, but does have an element of order 8. Now, on the other hand, the third group doesn't have elements of order 16 or 8. It does have elements of order 4, but that's also shared by the group that appears below it in the list. However, these groups differ on the numbers of elements of order 4 that they have. And then finally, the last group in the list doesn't have elements of order 16 or 8 or 4. So if the group of order 16 you were interested in only had elements of orders 1 or 2 and no higher orders, you would know that you were looking at a group isomorphic to Z2, direct product Z2, direct product Z2, direct product Z2. But let's apply this. We can tell which direct product of prime power order cyclic groups a finite abelian group is isomorphic to by looking at how many elements there are of each order. Let's take that and decide which of these possibilities is isomorphic to this group. As we look at the Cayley table, we'll notice that the element O is the identity of the group. We'll notice that B has order 2 because the identity is sitting there. And in fact, as you take a look at this, every element of the identity has order 2. And that tells us that this group is not Z8, which has an element of order 8. It's not Z2, direct product Z4, which has an element of order 4. In fact, the only group it can be isomorphic to is this last group. Now, as we can see here, knowing ahead of time the complete list of possibilities to which a group can be isomorphic, that list is given to us by the fundamental theorem, it makes it very easy to determine which group we are looking at. Given any abelian group, we can just look at the orders of the elements, and we can rule out everything except for the correct group. That makes the fundamental theorem pretty useful and pretty valuable and pretty fundamental. Well, the last application of this fundamental theorem we'll mention in this video deals with Lagrange's theorem. Now, you'll remember that Lagrange's theorem said that for any group of order n, if H is a subgroup of G and H has order D, then D has to divide n. Now, the converse of Lagrange's theorem is not always true, but for abelian groups, it is. In any abelian group G of order n, if D is any divisor of n, then there must exist a subgroup H of G having that order D. Now, knowing that the group G has to be isomorphic to a direct product of cyclic groups of prime power orders, you might be able to take the structure of such group and build a subgroup of any given order you wanted purely by construction. Another approach to proving this would be to use induction and factor groups. Now, either proof is interesting. I encourage you to look at how you would prove it. But as we leave our discussion of the fundamental theorem of finite abelian groups, we'll mention that because we understand direct products and because we understand cyclic groups very well, it's possible to explain everything in fairly short order, any question that can be asked about finite abelian groups. And so as we look for the next new area of group theory, our attention will inevitably turn towards either infinite groups or to non-abelian groups. There are a lot of questions left to answer in this realm and a lot of group theory left to learn.